Hey everybody, welcome to video number 6 of our journey of exploration, discovery, and joy in that most beautiful subject in math, complex numbers and complex analysis. A big part of what makes math beautiful is when you can put different subjects together. I want to do that here in video number 6. I want to take the ideas from video number 4 and video number 5 and merge them together to explore something new. Our ultimate goal is to define the distance between two complex numbers and then to use that to describe some special kinds of sets in the complex plane. To get there, we start by reviewing. First of all, given a complex number z equals x plus iy in the set of complex numbers c, we can define the modulus of z, denoted by the absolute value symbols, and it's also sometimes called the absolute value of z, as the square root of the real part x quantity squared plus the imaginary part y quantity squared. Geometrically speaking, if we plot z in the complex plane, this quantity represents two things. As a point, it represents the distance between this point and the origin. That can be seen by applying the Pythagorean theorem. Draw a right triangle, label this side x, this side y, and this side by the Pythagorean theorem will have length square root of x squared plus y squared. That will be the distance between z and the origin. Also, if we think of z as a vector, an arrow going from the origin to that point, this quantity also represents the length or magnitude of that vector. As a simple example, we saw that the modulus of 4 plus 3i turns out to be a nice number. Take the square root of 4 squared plus 3 squared. That's the square root of 16 plus 9 is the square root of 25 is 5. The modulus of the complex number 4 plus 3i is 5. As a point in the complex plane, that's its distance to the origin. As a vector, it's the length of the arrow. We've already seen some properties of the modulus. Let's write them down to be a little bit more thorough here in this video. Properties of modulus. One property that you can write down is that it is a real number that's always greater than or equal to 0. If z is any complex number and I take its modulus, when I write this kind of inequality, I am implying that the modulus of z is a real number and it's not negative. It's greater than or equal to 0. Why? Well, just take a look at the equation. And by the way, notice there's no I in this equation. I'm taking the real and imaginary parts separately as real numbers, squaring them each individually, adding the results, and taking the square root of that. X squared plus y squared, no matter whether x and y are positive or negative, is a quantity that's greater than or equal to 0. And you take the square root of such a quantity, you get a quantity greater than or equal to 0. Moreover, also, the only way you're going to get a modulus equal to 0, the only way the modulus of z is 0 is if z itself is the number 0, which I can think of as a complex number, 0 plus 0i. Think about that. The only way this quantity is ever going to be 0 is if both x and y are 0. No other time. In video number 4, we saw a second property. We saw that the modulus of lambda times z, where in video number 4 I assumed lambda was actually a real number here and z was an arbitrary complex number, is the modulus of lambda itself, or you could say the absolute value of the real number lambda, times the modulus of z. This is true for all real scalars lambda, this upside down a means for all, and for all complex numbers z. This actually turns out to be true even when lambda is a complex number, but we haven't talked about that yet. We haven't proved that. We did talk about this in video number 4, and I'm restating it here. A third property that's something new but real important is called the triangle inequality. Triangle inequality. And that says if you've got two complex numbers, z1 and z2, and you add them, and take the modulus of the sum like this, the modulus of z1 plus z2, that the result will be less than or equal to the sum of the moduli is plural of modulus, of z1 and z2 individually. We will eventually prove this, not anytime super soon, but eventually. At the moment, however, let's see that this makes sense if you think about the geometric meaning of complex number addition. So once again, we draw a complex plane, real and imaginary axes. Let's think of the complex numbers as vectors. Let's pretend this is z1. I can then also draw z2. I could draw it here, but remember with vectors you can also translate the vectors. I can take z2 and translate it over here so that its tail, its starting point, is at the head of z1 to get a vector like this. That, as an arrow, has the same direction and length as the original arrow. We can think of either arrow as being z2. And then we saw in video number 3, actually, that the sum z1 plus z2 can be thought of as being this arrow. There is z1 plus z2. And you can see visually that the length of z1 plus z2, the modulus of z1 plus z2, is indeed smaller than the sum of these two lengths of z1 and z2 individually, effectively saying that the shortest distance between the origin and this point here is along the straight line between them. It's a pretty intuitive statement. But this is a pretty important fact in complex analysis and indeed in any kind of analysis class. These properties are really called properties of norms. I called it here properties of modulus, but you can also say properties of norms. That's another word that connects this subject to other subjects in math. When you have vector spaces that have a length or distance defined by these kinds of properties, you call it a norm, and those are called normed vector spaces. So C is a normed vector space, or sometimes it's called a normed linear space. That's important in lots of applications as well. Anytime you have a norm, it leads to the notion of a distance. So now we're going to talk about our main goal here, the distance between two complex numbers. Oh, let's call them z and w in the complex numbers. Let's say z equals x plus iy, and w equals, say, u plus iv. By the way, these letters zw, x and y, u and v, and of course I, the imaginary unit, are very commonly used in complex analysis. What is the distance between z and w? Often written d of z comma w. You can define it using the modulus, which again is also called a norm. How? It's the modulus of z minus w. Does that make sense? Well, let's think about it a few different ways. Along a real number line, if you were thinking about z and w as being real numbers, pretend z was 7 and w was -3. Let's pretend this is z and this is w. What is the distance between them? This formula does give you the right answer. The modulus of 7 minus -3, you could again call that the absolute value, is the modulus or absolute value of 10, which is 10. And you could do it the other way around. This is symmetric in z and w. You could do -3 minus 7 instead and take its absolute value. That's the absolute value of -10, which is also positive 10. And indeed, geometrically, you see that is the distance between z and w. But it works in the complex plane as well, and it even makes sense. Let's go back to drawing another picture in the complex plane. There's our real axis. Here's our imaginary axis. Pretend z is right there and w is right there. I'm drawing them as points. I'd like to effectively measure this distance between these 2 points. How could I do that? I could think in terms of vectors. Here's the vector for z. Here's the vector for w. We saw in video number 5 that you can draw the vector for z minus w as a vector connecting the point for w and the point for z. That arrow right there represents z minus w. The modulus of that quantity, its length, I could also translate it down here. That's also z minus w. The distance between this point and the origin is the distance between these 2 points for z and w. It makes intuitive sense. As an example, we could try to find the distance between, say, 3 plus I and 1 plus 2i. By the way, I'm doing these seemingly for always points in the first quadrant of the complex plane, but all these formulas work no matter where you are in the complex plane. That'll be the modulus of the difference, 3 plus I minus 1 plus 2I. To go ahead and compute this, go ahead and do the subtraction. Subtract the real parts, 3 minus 1 is 2. Subtract the imaginary parts, I minus 2I is negative I. We get the modulus of 2 minus I. That'll be the square root of 2 squared plus negative 1 squared. Square root of 4 plus 1, square root of 5. 5 is not a perfect square, so that is an irrational answer, but it is the distance between these 2 points in the complex plane. Distances also satisfy certain important properties that are worth writing down. Properties of distance. And by the way, just as modulus has another name in general called norm, distance has another name in general called metric. What are properties of distances or metrics? One property is that, well, you, once again, don't get a negative number. It's a real number that's non-negative. That's basically, essentially, this property here. The distance between any two complex numbers z and w is greater than or equal to 0. And also, you could say the distance between z and w is 0 if and only if z actually equals w. Okay, these two properties correspond exactly to this property, these two properties of modulus up here. I'll let you go ahead and think about that. You could write down a property related to scalar multiples here, but it's not typically done with metrics, because when you talk about metrics in general, you aren't necessarily talking about vector spaces. But another property that can be written down is that the distance, the metric, is symmetric in z and w. It doesn't matter which order I do these things in. The distance between z and w is the same as the distance between w and z. That reminds me, as far as verifying that, we could certainly write this in terms of the real and imaginary parts here. I could have written, this is the square root of, what would the difference be? It would have real part x minus u, so x minus u would need to get squared. And imaginary part y minus v, so y minus v would need to get squared. That's a quantity that if you switch around the roles of x and u, and you switch around the roles of y and v, you'll get the exact same quantity, because of course when you square a number and it's negative, you get the exact same answer. So there's another property of metrics, and there is once again a triangle inequality. Though the triangle inequality for metric spaces is a bit more complicated looking. Triangle inequality. You have three complex numbers in this case. The first two we'll call z1 and z2. The distance between z1 and z2, if I've got a third point, any other third complex number z3, is less than or equal to the sum of the distances between z1 and z3 and z2 and z3. Again, it makes intuitive sense if you draw these anywhere you want, pretending this is the complex plane. The distance between z1 and z2, that distance right there, is less than the sum of these two distances right here. This can be proven as a consequence of this triangle inequality, though it is a little trickier than you might think at first. Okay, so that's properties of distances, metrics. Distances can be used to describe, for example, circles in the complex plane. If we talk about the set of all points z in the complex plane that satisfy the property that, for example, the distance between z and, let's say the particular complex number 3 plus 2i equals some positive real number, call it r. That's a positive real number right there. That does describe a circle of radius r centered at the point 3 plus 2i. I hope that makes sense. We're talking about all points in the complex plane that have a constant distance of r to 3 plus 2i. There's 3 plus 2i right there. Got all the points in the complex plane that have a constant distance of r. Let's draw a circle. We pretend that circle has radius r. That is one way to describe the circle. You can relate this back to the modulus as well. You could say this is the set of all points in the complex plane so that the modulus of z minus 3 plus 2i equals r. This is probably a more common way to write it. By the way, all these vertical lines sometimes get confusing, and so sometimes people put colons here instead of a vertical line there. We can think of this in terms of the x and y, real and imaginary parts of z as well. This is equivalent to the modulus of x minus 3 plus y minus 2i equaling r. Using the formula for the modulus, that's equivalent to the square root of x minus 3 squared plus y minus 2 squared equaling r. Square both sides, and you get an equation of a circle of radius r in a plane where you would label the axes x and y. And that's going back to our association between the complex plane with axes labeled real and imaginary with a real plane with axes labeled x and y. That is the equation of a circle of radius r. Other kinds of sets can seem a little bit more mysterious at first, but when you think about them carefully, you realize they can be easier than they look at first. We could talk about the set of points. I won't bother with set builder notation here. Satisfying this equation, set of points z in the complex plane so that the modulus of z plus 6 is the same as the modulus of z minus 4. What is this set of points? It's much simpler than you might imagine. Maybe you want to pause the video and see if you can figure it out. Here's the way to figure it out. The modulus of z plus 6 is the same as the modulus of z minus negative 6. So we're saying the distance between z and the number negative 6, which can be thought of as a complex number along the real axis, is the same as the distance between z and the number 4, which once again can be thought of as a complex number along the real axis. Thinking about that purely geometrically, if we mark 4 right here and negative 6 over here in the complex plane, we can ask, what are all the points in the complex plane that are equidistant between those two numbers? Right here and right here. I hope it's pretty clear. It's got to be a vertical line halfway between them. In fact, a vertical line at negative 1, real part equaling negative 1. And probably the simplest way to describe that vertical line is with equation x equals negative 1. Can we verify that algebraically? Let's see. This would be equivalent to x minus negative 6 or x plus 6 quantity squared plus y squared, the imaginary part here is 0, equaling from over here the square root of x minus 4 quantity squared plus y squared. Square both sides. Get x plus 6 quantity squared plus y squared equals x minus 4 quantity squared plus y squared. The y squareds cancel. Oh boy, yeah, our equation is not going to involve a y. Now go ahead and expand these things. X squared plus 12x plus 36 equals x squared minus 8x plus 16. The x squareds cancel. You only have a linear equation in x and y, in just x in this case. Add 8x to both sides. 12x plus 8x is 20x. Subtract 36 from both sides. 16 minus 36 is negative 20. Now divide both sides by 20 and get x equals negative 1, matching this one right here. As usual, we end with a couple fun Mathematica demos. This code right here will effectively compute and visualize the distance between complex numbers, which can be thought of as a distance between points, or the length of the displacement vector going between those points. I enter it, I get a picture that looks like this. There's my z, there's my w, either as points or vectors. There's z minus w. The distance between z and w is about 2.23607. I do believe I picked this one to be where the exact distance is square root of 5. It matches the example we did earlier. But because I use the locator command, I can move these things around. I can see how the vectors change, and I can also see how the distance change. We are measuring the distance between z and w no matter what they are. With this code, we can describe circles in the complex plane. Here's the code right here. I enter this, and I get a circle in the complex plane. It's the circle centered at 3 plus 2i with a radius of 1. I did parameterize this circle using cosines and sines effectively. That's what you see right here effectively. 3 comma 2 plus cos t comma sine t. You can use cosines and sines to parameterize circles. That's going to be real important in complex analysis. And I can see how I let t vary from 0 to 2 pi. The point moves around the circle. And it's also illustrating that I can think of points on that circle in a very natural way as the sum of two vectors, one vector going from the origin to the center of the circle, and another vector representing, well, the green arrow going from the center to any point on the circle, giving me a resultant sum in red that is effectively tracing out the circle as t varies. Kind of fun. Thanks for watching. Strength and honor to you. Have a good day.